In this video, we're going to look at another class called stack of integers. This is one of the most useful data structures that you will probably study and has many applications in computer science. In this slide, we see a UML diagram describing this contract that's going to exist between a program that's using the stack and the stack. We start with two private integers. One is an array of integers and the other is just an integer, representing in the first case the elements that are in the stack, and in the second case the number of elements currently in the stack. There are going to be a number of methods associated with the stack. Two of them are constructors. One of them is a Boolean that you can query to determine whether or not the stack has something in it or if it is empty. There's going to be a peek method that allows you to take a look at what's on the stack without actually affecting the stack. There'll be a pop method which pops things off of the stack. In other words, it retrieves their values and removes them from the stack. And a push method that does the opposite, puts elements into the stack. At any point in time, you can find out how many elements are currently in the stack by checking get size. So that method will tell how many elements are currently in the stack. Now you'll notice the comments off to the right-hand side of the UML diagram. Most of them are self-explanatory and just fine, and you'll be able to understand what they're saying when you read them on your own. But I'm going to call your attention to two particular lines which can be confusing in some way. And that is the third and fourth line dealing with the constructors. The first says constructs an empty stack with a default capacity of 16. And the next one says constructs an empty stack with a specified capacity. There could be room for confusion here. Generally, when most people implement stacks, they do so in such a way that the stack has some limited size and you can only put things in the stack until it fills up and then there's no more room. It seems from the wording that you see here that we can either create a stack that can only hold 16 items, or we can make a stack of some specified other capacity, but it looks like that's how big it is and it can never change. What's not clear from what we see in this slide is that the implementation is actually going to support the stack automatically growing in size whenever it's about to run out of space. So what will happen then is that this is not really a default capacity of 16, but it's a default initial capacity of 16. And likewise, when you specify some other initial capacity, it's just that. It's an initial capacity. It's not a final capacity. So whether you start with 16 or whether you start with some other size that you choose, the fact is that once that stack fills, it won't simply be filled and can't take any more, but automatically it will, as it turns out, double in size. And every time it runs out of space, it will double in size again. So that may not be clear when you look at this UML diagram and the description. But now you know. That's what we're going to expect. In case you aren't familiar with a stack, we'll take a brief look at how it works. So in this diagram, on the top row in the far left, you see what is initially an empty stack. And you'll notice there's a data element called data1 that's being inserted into the stack. Moving on to the right, then we have a stack containing data1, and along comes element data2 also to be added into the stack. To the third diagram now, that is second from the right hand, we now see that the stack contains data1 at the bottom, data2 on top of that, and here comes data3 along to go into the stack as well. And then ultimately in the last diagram in the top row, you see all three data elements now stored in the stack, data1 at the bottom, data2 on top of that, and data3 at the very top of the stack. The stack works in such a way that we do not have access to the elements below the top element. So right now the only accessible data element in the stack is data3. The process of putting those data elements into the stack is known as pushing onto the stack. So again, starting through this series of 4 diagrams left to right, we begin with an empty stack. We push data1 onto the stack, and now we have a stack containing just data1. We push data2 onto the stack. Now we have a stack containing data1 at the bottom, data2 at the top, and now we push data3 onto the stack. and we're done pushing. We've pushed 3 elements onto the stack. Moving to the bottom row, we then begin to pop elements off the stack. So we have a stack containing data 1, data 2, data 3. Data 3 is at the top, and we pull that off of the stack now. Alternative term to pulling is popping. So some sources will refer to this as popping an element off the stack, and some will refer to it as pulling an element from the top of the stack. So in any case, data 3 is now gone, pulled or popped, as you prefer, and all that's left in the stack on the bottom row, far left, is just data 1 and data 2 now. At this point, only data 2 is accessible. So if we pop or pull an element off the stack, it's going to be data 2. This is in the middle diagram on the bottom row. And now data 2 is popped off the stack, leaving just data 1. And then finally, on the far right-hand side of the bottom row, we pull the last remaining element out of the stack, or we pop it off the stack. Data 1 is now gone, and we now have an empty stack. So that is the way a stack works. In this next slide, we see a picture that captures the implementation of a stack. We're going to be using an array in our implementation, and so you see this array is called elements and is subscripted from 0 upwards. So the bottom of the stack then is indexed by index 0. The next position in the stack is indexed by index 1, and so on up to capacity minus 1. Remember what I said earlier about the capacity of the stack. It's not a hard and fast capacity such that we could actually fill the stack up and run out of space. Because in the implementation, what is going to happen is as soon as that stack fills up and we don't have any more room and we want to push one more element on the stack, the implementation is going to automatically make the size of the array double, increasing the space that we have by a factor of 2. There's no mechanism by which it will shrink afterwards, so it simply will remain at that new size until again in the future, if it happens to run out of space again, it will simply double again. And every time it runs out of space, it will double in size. We have the ability to set its initial size, and if we don't ask for a particular initial size, it's going to be set to an initial size of 16. If we take the default of 16 and our stack is about to overflow, then rather than overflowing, what will happen is it will simply double from 16 to 32. And we can continue using it then at that new capacity. And if it happens to fill up yet again and is about to overflow, then we'll double it once again, this time from 32 to 64 elements, and so on and so forth. So we can never run out of space in our stack, at least not until we run out of memory on the machine that we're running this program on. That might be a little bit unusual. In most implementations of a stack, there is the concept of overflow where there's a fixed maximum size, and at some point you can fill the stack up all the way, and if you attempt to put one more element in it, we would say the stack overflows. But in the implementation your author gives in the textbook, that cannot happen, as I said, unless the machine outright runs out of memory completely. Other than that, you can always put more things in the stack because as long as there's more memory available, we will use it. The size of the stack represents the current number of elements in the stack, whereas the capacity of the stack represents the space available for more elements. The capacity isn't really a restriction, however, because as I emphasized already a number of times, as soon as you run out of capacity, you double the capacity, and so it winds up never being an issue. And I guess now we can go out to the IDE and actually look at the implementation of this stack.